Hi. In this video, we will see another example which will eventually be an application of the optional stopping theorem. In that example, two people will be playing a random game. In the previous years, I used to call those people Alice and Bob, but this year is special in so many ways, so our players today will be called Bella and Mark. Hi, guys.
Hi. Hi.
So tell me what your game is about.
We are rolling a die.
How many times?
Many times.
So Mark and Bella are rolling a die repeatedly. And what outcome are you waiting for, Bella?
I'm waiting for 666.
So Bella is waiting for the numbers 6, 6, and 6 to occur consecutively. What about you, Mark? Which numbers are you waiting for?
4, 5, 6.
Okay, so Mark has a different combination. He wants 4, 5, and 6 to occur straight after each other. Which shouldn't make much difference, should it? As all the numbers are equivalent as far as the die is concerned. So anyway, this is the setting, and the winner is whoever gets their pattern first. So Mark and Bella, who do you think is going to win?
Me!
That's the spirit. What do you think, though? Who is more likely to win? Bella with her pattern of 666, or Mark with his pattern of 456? Or are their chances equal? We'll find out in the live class. Meanwhile, if you have time, you might want to write a little code to simulate the game. For example, you can try to compute numerically the chances of winning for each player, or you can also compute the average waiting time for each pattern. And during the live class, we will see to what extent the numerics agrees with the theory. Good luck with that, and see you in the live class.
After the live class.
Okay, we have learned by now that the patterns do not have equal chances to occur. In the live class, we ran a simulation and saw that the pattern 456 wins in roughly 55% of the cases. We also computed numerically the expected waiting time for each pattern and saw that it is significantly shorter for 456. So 456 seems to be the winner. Then we discussed whether we could make this rigorous, and indeed we found a way to compute the expected waiting time for each pattern using martingale techniques. In this video, I will summarize what we did and add more details and explanations. Now, what we will do, we will compute the expected waiting time separately for each pattern. For each pattern, we will construct a fair game, a martingale, and we will stop it at the time when the pattern first occurs. The structure of the martingale will be chosen very specifically in such a way that it gives us the expected waiting time of the pattern at the end. So let's see what our game for each pattern is going to be. First, let's do this for 666. We will have infinitely many players. Every day, a new player joins the game and invests £1. Each player is playing for at most 3 days. The day she joins the game, possibly the next day, and possibly the day after. So let's see what the game looks like for the player joining on day N. So here she is. Here's her £1, and here are the 3 days when she will be playing: day N plus 1, and day N plus 2. So let's see what she's doing on day N.
On day N, I bet £1 on 6. If the die rolls 6, I win £6 and keep playing. If the die does not roll 6, I lose my money and quit the game.
So the winning amount of £6 is chosen in such a way as to make the game fair, because the probability of rolling 6 is obviously 1/6, and it would be fair if she won £6 if she had invested £1. Okay, so let's see what she's going to do on day N plus 1.
If I am still playing on day N plus 1, I bet £6 on 6. If the die rolls 6, I win £36 and keep playing. If the die does not roll 6, I lose my money and quit the game.
So this is the same game basically, but with the stakes increased by the factor of 6. So it's still fair. So let's see what she does on her final day.
If I am still playing on day N plus 2, I bet £36 on 6. If the die rolls 6, I win £216. Yippee. If the die doesn't roll 6, I lose all my money. Oops. In any case, I quit the game.
And again, this game is fair because it is easy to see that 216 is equal to 6 cubed. So this is our multiple player fair game. And since it's a fair game, we know that the difference between the total winning, total means by all players who has joined the game by the time n. So we know that the difference between the total winning and the total investment is a martingale. And then the optional stopping theorem tells us that if we stop this martingale at a reasonably nice stopping time, then the expectation of the stopped martingale will be equal to 0. And in other words, this means that at any reasonably nice stopping time, the expected total investment is equal to the expected total winning. So let's talk about the total investment first. It is actually very easy to understand because by the time n players have joined the game and each invested £1, so IN, the total investment, will simply be equal to n. And in particular, IT will be equal to t. And this means that for any nice stopping time, the expected value of that stopping time is equal to the expected winning by that time. And in particular, we are interested in the stopping time T666 when the pattern 666 occurs first. And we now know that to compute its expected value, we just need to understand what the expected winning is by the time T66. Okay, so let's see who wins what by the time T66. So let's look at the following picture, for example. So you see a possible development of the game. You see 666 has occurred and the game was stopped after 8 days. So let's see, for example, what the winning of the first player is. She wanted the die to roll 6 on day 1. This didn't happen, so she lost on her first day of play. So what about the player number 2? For her, the game started better. She had 6 and 6 on her first and second day of playing, but then she lost on the third day and she ended up with nothing. And it's easy to see that the same argument, the same logic applies to all players except possibly the last 3, because for all of them, the game is over by now. And we know that none of them has experienced 666 over 3 days. So all those players have lost. Now, the main winner is the next player, the third last player, because it's her who had the combination 666 during her 3 days. So she gets 6 cubed pounds. But also the game wasn't too bad for the last 2 players. It is not over yet for them. And the second last player is sitting there with 6 squared pounds after 2 days of playing. And the last player is having 6 pounds. So the total winning by the time T666 happens to be 6 cubed plus 6 squared plus 6. And we don't even have to take the expectation. It's just a deterministic constant. So this answers our question, what the expected waiting time of the pattern 666 is. It is 6 cubed plus 6 squared plus 6. Okay, now let's see why the situation is different for the pattern 456. So let's try and design the game which would help us find the expected waiting time for 456.
Our game is very similar. The only difference is that we bet on 4, 5, 6 instead of 6, 6, 6.
So you see, the game is indeed very similar. The stakes are the same. The winnings are the same. It's simply the desired die rolls which are different. So this means most of our logic applies. And in particular, it is true that the expected waiting time of 456 is equal to the expected total winning by that time. And this suggests that something should be different about the total winning in the case of the pattern 456. So let's see what it might be. So this is how the game may have developed. Again, you see the final combination is 4, 5, 6, and this is when the game was stopped. So what can we say? First of all, by the same logic as for the pattern 666, we can say that all players, except possibly the last three, have lost, so they get nothing. Again, by the same logic as for the pattern 666, the third last player is the main winner, and he gets 6 cubed pounds. But the situation is pretty grim for the last two players, because if we look at the second last one, for example, we see that he wanted the die to roll 4 on his first day of playing, but the die rolled 5, so he lost. And equally, the last player has lost because he wanted to see 4 on his day, and the die rolled 6. So unlike in the 666 scenario, here the last two players are also losing. And therefore, the total winning and the total expected winning is equal simply to 6 cubed. And this is the answer to our question, what the expected waiting time of 456 is. It is 6 cubed. And in particular, you see that it is smaller than the expected waiting time of 666, which was 6 cubed plus 6 squared plus 6. And therefore, in our original game, the combination 456 is more likely to win. It's more likely to occur first. Okay, so this is the end of the fun part, but we still have to do the boring part. We still have to justify everything we have just said. So we have to explain why our game is a martingale. We have to prove that our stopping time is almost surely finite, and we have to explain why the optional stopping theorem is applicable.
The boring part.
Welcome to the boring part. I will only do it for the pattern 666 because 4, 5, 6 would be the same. I suggest we start by proving that our process, our multiplayer game, is indeed a martingale. So let's denote by epsilon n the sequence of independent die rolls. We are interested in the process xn, which is the difference of the total winning up to time n and the total investment up to time n. And we agree that the total investment in our game is n because each player invests £1. Now, we want to write wn, the total winning, as the sum of the winnings of all players. And I will treat the players for whom the game is over differently from the last two players who are still playing. So for those who have finished the game, I will write the sum from 1 to n minus 2. So each of those players ended up either with nothing or with 6 cubed pounds. And 6 cubed it was if and only if they experience the combination 666 during their 3 days of playing, which means epsilon I was 6, epsilon I plus 1 was 6, and epsilon I plus 2 was 6. Similarly, for the second last player, they have played for 2 days for now, so they are having either 0 or 6 squared, and 6 squared happens if the last two rolls were 6s. So epsilon n minus 1 was 6 and epsilon n was 6. And for the last player, it's either 6 or nothing, and 6 happens if and only if epsilon n is equal to 6. So now we want to prove that xn is a martingale. Clearly, everything is bounded here, so xn will be integrable. It will be obviously adapted to the natural filtration of epsilon n. So all what we need to show here is that the conditional expectation of xn, which is, we remember, wn minus in, I'd better write it as minus n. So we want to prove that the conditional expectation of xn, given the information from the previous day, so the sigma algebra fn minus 1, that this is equal to xn minus 1. And we remember here as well that xn minus 1 is wn minus 1 minus n minus 1. So as usual, what we will do, we will look at all those epsilon n's, epsilon i's appearing everywhere, and we will remember that all of them except the last one, except epsilon n, are measurable with respect to this sigma algebra. So where do we find epsilon n, which is not measurable? We find it here, we find it here, and we find it in the last term of this sum only in the term number n minus 2. So this epsilon will be exactly epsilon n. But all the previous terms in the sum simply do not have epsilon n. This means all the previous terms I can take out of the conditional expectation. So I'm going to put them here and change the upper index to n minus 3. So this gives me this is what gives me this sum except its final term. Now let's deal with the final term. The final term consists of 3 cubed. Also, it consists of the product of two indicator functions corresponding to epsilon n minus 2 being equal to 6 and epsilon n minus 1 being equal to 6. And then the last one is the indicator function of epsilon n being equal to 6. And since it is independent of the past, the conditional expectation becomes the usual expectation. So this is what happens to the whole sum. Now, what happens to this term here? Very similar thing. We keep 6 squared. Then we keep one of the indicators, which is epsilon n minus 1 equals 6. And we compute the usual expectation of epsilon n equals 6. And same story for the last term. It is 6 times the expectation of the indicator function of epsilon n equals 6. And we should not forget that it's not just wn, which we are computing the conditional expectation of. We also have this minus n here. So let's not forget minus n. Now, we want to prove that it is equal to wn minus 1 minus n minus 1. Wn minus 1 is given by this formula where every n is replaced by n minus 1. So let's see, this term is exactly what we are looking for because it looks like this sum here with n replaced with n minus 1. Now, what happens to the next terms? First of all, these expectations are all the same and are very easy to compute. It's simply the probability of the die rolling 6, and it is 1 over 6. And then we can cancel 6 here with one of the 6's here, 6 here with one of the 6's here, and this 6 and 6. And then this term looks exactly like this one with n replaced by n minus 1. This term looks like this one with n replaced with n minus 1. This is equal to 1, so together with this term, it gives me n minus 1. So it is indeed true that this conditional expectation is equal to x n minus 1. So our process is indeed a martingale. Now we look at the stopping time, and our stopping time is T666, so the first time, the infimum over all n, such that epsilon n minus 2 equals 6, epsilon n minus 1 equals 6, and epsilon n equals 6. And we need to justify the formula that the expectation of the expectation of our martingale x at time t666 is equal to the expectation of this martingale at 0, which is 0. So let me say this explicitly. So we need to justify this, and the justification comes from the optional stopping theorem, which I have written here. So it tells us that if we have a martingale, and we have just proved that we do have a martingale, and a stopping time. I'm not going to prove that this is a stopping time. It's quite obvious, and we have seen similar examples before. So we need to justify that it is almost surely finite, and we need to check that one of these three conditions is satisfied. Then we will be able to say that this formula is true, and this is what we want. Now let's see which of the three conditions might be true. So is our stopping time bounded almost surely? Well, not really, because we can't be sure that 666 will roll before any fixed time. Maybe it will take ages until we get it. So no. What about the third property? Is our martingale bounded? So let's look at it again. So here it is. Well, the winnings are bounded, but if our game goes for a long time, then this term drags it down actually infinitely far. So the total investment is not bounded, and therefore xn is not bounded. So we can't use property 3 here, or condition 3. So our best bet is condition 2. And here we need to check two things. We need to check that the increments of our martingale are bounded, and we need to check that the expectation of our stopping time is finite. And by the way, if we manage to do this, we don't need to prove that t is finite almost surely, because finite expectation implies being finite almost surely. So this is what I will do now. I will show that the increments of xn are bounded, and I will show that the expectation of t is finite. So let's do the first thing, the bounded increments, because it's easier. So xn plus 1 minus xn. So by how much the winning can change from between 2 days, and by how much the investment can change in between 2 days. Well, it's easy with the investment. It changes by exactly 1. What about the winning? There are only 3 active players between any 2 days, and each of them cannot win more than 6 cubed. So a generous bound would be to say it's less or equal, the total win, so the change in the winning is less or equal than 3, which is the number of active players, times 6 cubed. And this bound isn't sharp by any means. So the increments are bounded, and now why is T666 finite, integrable? So let's write the expectation of T. Let's write down the formula. So T is never less than 3. So I have to sum over k from 3 to infinity, and I'm summing k times the probability time of T being equal to k. And then I want to estimate that probability, not in a very precise way, just in a way which allows me to prove that this series is finite. So what I will do, I'll draw the timeline. And I put down some times like 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on. And then somewhere there will be my time k. And then what I will do to estimate this probability, I will split the times into groups of 3. So this will be my first group, this will be my second group, this will be my third group, and so on. And then I only need a bound for the probability. I don't want to compute it precisely. And therefore, what I'm going to say, well, if I know that my t is equal to k, I definitely know it was not a 6, 6, 6 here in the first group. So that was definitely not the case, right? I also know that I didn't have 6, 6, 6 in the second group, right? For the very same reason, because my t happens to be k and not 6. So 6, 6, 6 does not occur here, and similarly, it doesn't occur in the third group. So what I will do, I will say, well, how many groups of 3 I have not including k? It is k minus 1 over 3, and then I need to take the integer part if I want to have the number of groups. And then what is the probability of not having 6, 6, 6 in each of the groups? Well, it is how many combinations I have there, 6 cubed, and how many do I exclude? 1. So it will be 6 cubed minus 1. Raised to the power, which is the number of groups. And this series converges. It's quite easy to see this because this term is taken from the geometric series. So you see this number is less than 1. And this term doesn't change much. You can use the ratio test to prove it if you don't see it straight away. So this is how we prove that t is integrable, that t has finite expectation. So that's the end of the proof. That's the end of the justification. And now we know for sure, we have proved it, that the combination 4, 5, 6 is better than the combination 6, 6, 6 for our original game.